Hi, good evening, and welcome to the lecture on wavelet transforms, an application of wavelet transforms for telemedicine and multimedia. While wavelet transforms is a very mathematical topic, and nearly all the books written have been by mathematicians, this particular lecture is going to target the application of wavelet transforms, and in order to learn the mathematical details behind the wavelet transforms, you should be able to get that in the book by authors like Mallet, etc. Real signals vary with time. Their properties change with time. When you want to do Fourier transform on a signal, you assume that the signal property is remaining the same for the entire window that you are working with. So, if you have a signal and you take the spectrum, you are assuming, let's say that the spectrum looks like this. You are assuming that this is the spectrum for the entire duration of your measuring. But that may not be true. In fact, that in real signals is not true. Audio signals, biosignals, etc. So what you need to identify is not only the spectrum at any specific time and the change in spectrum that is happening. That itself is a property of that signal. One of the techniques used is STFT, short-term Fourier transform, which measures the Fourier transform for a short time window. But according to Heisenberg's property, you have a limit to the resolution in time and frequency. Thus, when you do this, you can have narrow time windows. This is time, and this is frequency. And this way, you have the spectrum of the signal for each of these time windows. But the resolution in frequency is wide. On the other hand, if you want to change this, you might be able to make it like this. So what have you done? You have now increased the resolution in frequency domain, but now your time window has become big. So you have an uncertainty whether the change of spectrum happened here, or here, or here. You're taking this and you're approximating it more in time domain. But now there is a way out which is called wavelets. Wavelet transform. With the help of this, it is possible to control the resolution you want dynamically. In STFT, you are either stuck with something like this or something like this. But with wavelet transform, you can get the combination of this as you require. Let's consider what is a wavelet transform. If I have the original signal and I break it up into average, the approximate, the trend, various names, and the detail or the difference. Then I break it up again, and the detail, and again, and the detail. Now this is thus my original signal, f of t, has been decomposed. And as you can see that at each level, I have downsampled it by 2. So my frequency content of this, the low pass filter, is now halved and further halved. And same for my band pass filter. Wavelet transform of a signal f of t will measure the change of the spectrum of f of t over time. What do? We have the wavelet function. Now this wavelet function is something like this, a wavelet. And if I was to take this and translate it, this is at some time, I can move it to another time. I can scale it. I can make it narrower, or I can make it wider. The narrower, the higher the frequency, the wider, the lower the frequency. So I can cover different frequencies and different locations. Now, the original function is z of t. This becomes where u is my translation, s is my scale. And to get the wavelet transform of the original signal f of t, I take the correlation of the two using the convolution formula. That is, the wavelet function of f over u and s is equal to the integral f of t conjugate t minus u over s. That is simply to get the scale right. Now this is now the information of the original signal f of t as a function of translation, in other words at different times and different scales for information in different frequencies. Let's consider a simple example for a scaling function, which is simply like this. This is what you saw as an averaging method. This is also called the Haar transform. So this is a scaling function for the Haar transform, and if you consider that the wavelet transform of the same would be now, and you can see that this is where I've translated it, the scaling function original, and I've scaled it, so it's become half. So it's covering double the frequency, and I've moved it this way. So this is just an example to show you how my wavelet transform scales and translates. Now this, of course, is the simplest wavelet transform. You would normally use much more complicated wavelet transforms than this. Wavelet transform in the real world, how do you achieve it? You can't do those equations all the time. So what is simply is that the wavelet transform in itself is the impulse response of a filter. So you have this corresponding to an impulse response. Now this has got an impulse response which will be that of a bandpass filter. And if you have a bandpass filter, you also need, corresponding to that, another function which is for a low-pass filter. Now this is wavelet. So this is called the scaling function. Now, the combination of that we use to decompose the signal. What do we do? Now, if this is my net signal, limited by the sampling frequency of the original signal, I pass it, I decompose it in the middle. So this corresponds to the wavelet and this corresponding to my scaling function. How do I achieve that? How can I do it in real world? Now, what I do is that I pass the signal, original signal, through the filters, the high band pass and the low pass. Output of this is called my trend, or also referred to as approximate. And this becomes my detail. And this now, if I change the sampling rate of the signal, original signal, to half of this, then using the same filters, same impulse response, all I've done is I've scaled it. And I pass it again through a band pass to get detail again, and trend or approximate again. So what I've done is, before I've come here, I have downsampled my signal by a factor of 2. As we are using digital filters, because digital filters are over a period 0 to 2 pi. They do not have an absolute number for the frequency, and this corresponds to this sampling rate. So by using the same filter, but simply changing my sampling rate, I can use the same filter again and again and break the signal down from the original signal to my approximate and detail, approximate and detail, approximate and detail, etc. This is the technique that is used in the commercially available wavelet techniques. One of the chief properties of wavelets, which is very important, is a multi-resolution capability. What you can do is that you can break this signal up and you can resolve it to whatever level you wish to. So let's start here. If we were to only use a scaling function, which is basically the low-pass filter, you have the entire signal, then you break it up, then you break it up, and then you break it up. Now this obviously is the grossest part of the signal, most approximate part of the signal, while this band represents the detail. Now, instead of using only the low-pass filter, the scaling function that we used earlier, if we use a combination of wavelets and scaling function, what happens is we get the scaling function represented by the V naught in the center, the wavelet outside, which is the band here. This is the higher detail, etc. So the entire signal is here. We've now split it at the level 1, which is W2 here, and the inside becomes the cross. The next step, we break it up into this, the approximate, and this becomes the detail. So this first level, this is the detail, and this is the approximate. Next level, we take this becomes the detail, and this becomes the approximate. Further, this becomes the detail, and this becomes the approximate. So we can decide what level we want to go to, and we have now decided that we've gone to the third level. So this becomes our approximate, and these are details 1, 2, and 3. Now, what the wavelet transform does in that multi-resolution capability is that it breaks down the signal, the original signal, from time domain into frequency domain at different levels. So here you see this is at wide time. So it gives you the approximate of the signal over the entire this duration of time, but with very small frequency windows. So this gives you how the signal is overall looking like. While here you get, for narrow periods of time, how does the spectrum change from here up to here. Out here you've lost the information in time. Out here you preserve the information of time. But the resolution and frequency has obviously come down. The areas of each of these have to be in accordance with the Heisenberg principle. Wavelet functions have the convenience, they provide the convenience that you can select the wavelets according to your application, according to the signal that you're working with, according to what you want out of it. But that comes with a baggage. Now you have to know how to select the appropriate wavelet function. So how do you do that? Of course, you can develop your own wavelet function depending upon the application, but that often might be time consuming. So one of the easier ways is that you can use the number of existing wavelet functions that are available and select the appropriate one depending upon your application. How do you do that? So some of the properties of the wavelet functions are: 1, the smoothness. This is dependent upon what is the order of the derivative that you can take. So the rth derivative of the signal, of the wavelet function. The second is the whether it is symmetrical or not. Now this is dependent upon how you want to keep the linearity of the decomposition. Third is the time and frequency support. Whether you want it narrow time base, narrow frequency base, or both. Now you can see this and this are opposing each other, and also this and this are opposing each other. So you have to select whether you are having to have an application where there's small changes in frequency or there's small changes over time. So the changes are very quick over time. You want to capture those little places where it happens, or the changes are happening over frequency. Very small changes are happening in the frequency and you want to capture them. The zero order, also called moment. What is the sharpness, the cutoff that you want? How quick you want the frequency cutoff to be of this particular properties of the signal that you're trying to capture. Again, this is related to your number 3. So, and also whether you would like it to be orthogonal. What that matters is that whether you would like to maintain the energy, whether you want to only decompose it or whether you want to bring it back. And that would depend upon your selection of this. This and this oppose each other. So you have conflicting properties, and hence you have to select your wavelet function depending upon the properties that you want to be able to measure. Whether you want to, most of the wavelet functions support multi-resolution, but still, if you want to deal with that, whether that is of importance. Again, another property that might be important is whether you would like to identify the translation invariance or not. Now, this is again certain properties that will come up, and based upon that, you have to thus select the appropriate wavelets. The number of available wavelets which you can use, you can also design your own ones, but the easiest ones you can get on tools like MATLAB, etc., are the HAR, the Dobeshi's, the Simlet, which is the symmetrical one, as it's evident, the Quiflet, and many more. Now, these are the ones that are commonly used and we'll be using for our applications. Why do wavelet transforms? What are the applications? Well, one of the chief applications is the fact that when you start with the signal, the original signal, and you decompose it into detail and approximate and detail, what has happened? Each time you downsample by 2, so you now hear 1/8 of the original signal. And this is approximating to your original signal. It has been found that in most of the signals, this has about 88% of the energy of the original signal, which means that you have not lost most of the signal, but have been able to reduce the data by 8 folds. This is massive reduction, and hence the application, or the obvious application of this is data compression. In fact, nowadays, nearly all the data compression techniques, whether it is related to audio, related to images, etc., are based upon wavelets, JPEG 2000. Now, the other interesting property is that it's been found that in most of the signals, these details are often what contain the noise. So if you get rid of this, what you're left with is the signal and with highly reduced noise. Thus, you have been able to denoise the signal. So you got the signal data compressed and denoised using wavelet transform, and a great advantage. Thirdly, you can also find is that signals have certain properties which can be used to identify those signatures in that signal. Voice of a person, something in the EMG of the person, something in an image of some image that is either in only some areas, like one detail might actually differentiate between my voice and someone else's voice. So if I can identify those kind of points, then rather than I compare the whole signal here, I only pick up what is relevant to find out the difference between two signals for the purpose of classification and identification. Another very important thing. So I have denoise, data compression, and classification, oblique identification. You will find that you are doing this when you are working on the assignment, where you are trying to identify the differences between two signals related to muscle fatigue. Thank you for coming for this lecture. Now, what we have discussed are the various properties of wavelet transforms, the kind of wavelet transforms that are available, some of the issues, applications of the wavelet transforms, as well as the basic fundamentals of wavelet transforms. Now you should have a look at the lecture, which is located on S Drive, and also go through some of the material which is recommended at the end of my lecture there. Thank you.